All right, learning goal number 5. Let's do it. Be familiar with the wave-particle duality and know the de Broglie equation. So we're just going to talk about this briefly in this review section, and I'm going to show a couple examples of some powerful objects that take advantage of wave-particle duality. Okay, let's find the slide. Here we go. So just kind of, like I said, a brief review on the dual nature of light. Light can act as a wave or as a particle. So one of the most common observations of light as a wave is the way in which it interferes with itself. So if you recall, when two in-phase waves add together, they add together constructively. So the result is a larger wave. When we have two out-of-phase waves, so in other words, where the minimum and the maximums are lined up, they will destructively interfere and cancel. So famously, this was observed in the double slit experiment, where if we shoot a light source through two narrow slits, we see a confluence of constructive and destructive interference as given by this screen. So the bright spots right there are where we would have constructive interference, and the dark spots there are where we would have destructive interference. So light also can behave as a particle. There are many, many observations of this. In the older literature, this is referred to as corpuscular theory, so that's kind of old. I thought it would be interesting just to put some of that old terminology in there. And a very simple observation of light acting as a particle is from the law of internal reflection, where if we shoot some incident photons at some reflecting surface, we will see the angle of incidence will match the angle of reflectance, which is what we would observe in just like a classical object, like a bouncy ball or something like that. Okay. So many, many other observations of light behaving as a particle, but this is an easy one to talk about for now. So I want to jump straight into our quantum stuff and discussing the de Broglie equation. And he famously said, if electromagnetic radiation behaves as a particle, could a particle in motion, such as an electron, behave as a wave? And as it turns out, yes. Electrons can also exhibit wave-particle duality. So this leads to the famous de Broglie equation, which we're going to see many times this semester. So that says the wavelength lambda equals Planck's constant divided by momentum. So if we break down those units for a second, Planck's constant is a joule per second. And recall momentum is mass times velocity. So let's write that down. That's the momentum of our particle. So standard units of mass are kilogram, and that of velocity is the meter per second. So we should keep going so we can distill this down to more simplified units. So remember, unit of a joule is the same as mc squared, kilogram, meter squared per second squared. So let's write all that down, kilogram, meter squared per second squared. And that's still times a second, and that's still divided by a kilogram times a meter per second. So as we can see, the kilogram and the kilogram will cancel. We have, let's see here, we're going to get this second cancels with one of these seconds, which cancels with the other second. And then finally, we've got a meter squared over a meter, which just reduces to a meter. So that gives us the proper units of wavelength. And so now if we notice here, the way this relationship works, the de Broglie wavelength of our particle is inversely proportional to its momentum. So particles that have a large momentum have a correspondingly short wavelength, right? They have a large energy. On the other hand, particles with low momentum have a long wavelength, or in other words, a small energy. Okay. So let's look at some consequences of this. And to describe this, I first want to just talk about the physics of diffraction. So this is the change in directions of waves when they pass through a small opening or around a barrier in their path. And the two pictures show what I want us to note most importantly about diffraction. There is more diffraction, or there is more change in direction as the opening becomes smaller, right? So you can see that opening in which we were shooting the light through in this case is much smaller than in the first picture. So we get a more divergent beam. So this is shown with light. Diffraction can also happen with electrons from the famous Davison-Germer experiment, which shows that scattering of an electron beam from a crystal, and there's a variation in intensity characteristic of interference constructively and destructively as these electrons are interfering with the atoms in the material. So we can take advantage of that effect to do what's called electron microscopy. So two different types right here, and we'll only talk about these briefly. There's the TEM, the transmission electron microscope, and the SEM, the scanning electron microscope. So as you can see, both start with an electron gun and an anode, which will allow electrons, right, to travel from cathode to anode. Those are focused into a series of lenses. And as we should note, these lenses are meant to focus electrons, not to focus light. So their construction is just a little bit different than optics, than light optics. Most notably, what I want you to see in the transmission electron microscope, our sample is actually right here. So that is our sample. So in the transmission electron microscope, electrons transmit directly through the sample. And this creates a diffraction pattern. So we might see like this pattern of where light, or I guess I should say the electrons, are coming through from constructive or destructive interference. And this allows us to work out a crystal structure if we work backwards and do some of that complicated math. On the other hand, in a scanning electron microscope, we typically use this to get an image. You can get a crystal structure from a scanning electron microscope, but that is less typical. It's more typical that we get an image from an electron microscope. And you notice now our sample is down here, and that's very cute. There's like a little bug down there, right? So we can use all kinds of different things to get images of. And so now what happens is the electrons backscatter off of that sample and creates an image on this backscattered electron detector. And that's all that I'll say about SEM for now.